Hello, my name is Nicholas Lopez, and I'm currently a junior in electrical engineering. And today my project is lattice dynamics and stability of cubic pseudobinary iron X, cobalt zero point 0.5 minus X, and titanium zero point 0.5. I worked on this project with Bethel Kamala and Dr. Jorge Munoz, both from the physics department. We used the Born-von-Karman model from lattice dynamics by calculating the phonon dispersion relations from the forces and took a look at the atoms that were displaced. So when we take a look at these structures, we usually see that imaginary frequencies show instability. So we wanted to kind of increase the stability of cobalt titanium. So we took a look at the stable cubic phase at about 40 Kelvin, whereas iron titanium is stable at all temperatures. So this was the basis of our project, and we wanted to see if we could increase the stability of cobalt titanium by adding some iron atoms into the mix. So this is a work by Art Ablard et al. You can see the band structure on the left shows some imaginary mode frequencies, which tells us some instability is going on. But what we're focused on is the density of states right here on the right. The density of states, you can see that with iron titanium on the top, it has a much lower Fermi energy at the Fermi level, whereas the other two are a little bit higher. So we wanted to see if we can add in some iron into with cobalt titanium, so we can reduce the number of electrons and reduce at the Fermi level. The methods used for this project were using lattice dynamics and PhonoPy, along with Quantum Espressable to take a look at the forces, but what we were doing is we were tricking PhonoPy by switching in iron for some cobalt atoms into Quantum Espresso. Note that the structure wasn't relaxed, so there weren't any local added effects, and on the figure at the bottom left-hand corner, you can see the phonon dispersion for the 16-atom supercell, which is the regular cubic structure. You can see some imaginary mode frequencies going on right there. Whereas if you take a look at the other phonon dispersion in the middle, with 6.25% composition of iron, you see that we have a more stabilized structure, almost little to no imaginary mode frequencies. Same kind of trend on the right where you have a 12.5% composition of iron. We wanted to see if the same trend would happen if we had a 128 supercell structure. So what we did is we also took a look at the phonon dispersions using the same method. The figure on the left shows a percent composition of 3.125% for iron. You can see that it does still have some imaginary mode frequencies, but not as much as the original structure. We also added in a little bit more percent composition of iron at 6.25%, and you can see that the imaginary mode frequencies are reduced. So you do still see those imaginary mode frequencies, and you might think, okay, why is the 6.25% on this one not have any, but this one does? That could be due to the phonon wavelengths and giving some mechanical instability. However, you do see the trend that as we add more iron into the mix, that the imaginary mode frequencies is reduced. Just to compare the structures a little bit, the cobalt atoms were replaced and selected in high symmetry arrangements, and notice like how we said at the beginning that the slab construction also showed an unstable structure. However, right here we have the 128 atom supercells, one with 4 atoms, the other with 8 atoms of iron, so that gives 3.125% composition on the left, and we have 6.25% composition on the right. What I'm currently working on is seeing if we can switch some iron atoms out with titanium and see if we can further increase the stability of the structure. So what I did is I took a look at the forces using a modeling application, and the first switch that I used, the problem with that one is that the titanium and the iron atoms were too far apart to look at anything. So with the second switch, however, I switched out these two atoms right here, the little gray one and this little orange one right here. They were a lot closer to each other so we could see what's going on. Again, we were using a 128 atom supercell with K points 4 by 4 by 4. However, we did get an error with the charge densities when we ran Quantum Espresso. However, we're very excited to see the results soon and see if maybe the structure was, the stability of the structure was increased. Lastly, for my conclusions, is that we were replacing cobalt with iron atoms in cobalt titanium. We saw that the more iron you add, it stabilizes the B2 cubic structure, so we didn't see those imaginary mode frequencies. And this happens because you're reducing the Fermi energy and reducing the number of electrons at the Fermi level. And we were able to see that trend with the different percent compositions of iron. My future work is to see what happens when we replace those titanium atoms with iron, see if it's further stabilized. We also want to test for relaxation to see if there's any added effects onto there. So we're very excited to see the results, but thank you all for attending today. Thank you all for your time.